Hi, this is James Banks. Today I'll be talking about my results for the final of the Fall 2021 Advanced Data Analytics 5550 Deep Learning with Big Data course at UNT Frisco. As you all know, there were 6 parts to this final, and I'll be covering each in this video. The primary focus of this final was to analyze images using convolutional neural networks and then to compare various models created using this technique to see how well they classified images. Part 1 involved selecting an image or audio file dataset. I chose an image dataset in that I'm considering using these types of techniques for a nonprofit I volunteer for as my capstone project in the spring. However, since that data was not publicly available, I elected to use the Stanford Dogs dataset. As the name implies, this dataset was developed as part of a Stanford University study and utilized at a workshop for image categorization at the IEEE Conference on Computer Vision and Pattern Recognition in 2011. The key aspects of this data is that it contains 20,580 labeled dog images of 120 different breeds. I've selected 5 of the images as a sample from the Chihuahua breed category on the right. As you can see, they show the dogs in various poses with different backgrounds and other distractions, including some with human hands or faces with the animal. The pictures are all in color with a depth of 3. However, the dimensions vary from image to image. For example, I found heights ranging from 188 to 500 and widths from 250 to 493 pixels. This did cause me some concern initially in that all the processing we have done to date was based on images that were a consistent size. However, a quick Google search indicated that images could easily be made consistent by using the resize function of the SKY image transform library. So that alleviated my concerns. There were a number of supporting documents on the website for this dataset. Most of the data was in semi-structured JSON formatted data files, which included lists of already split train and testing images. There was an annotation file, which included details about each image, including the dimensions, file name, classification of the image or the dog breed in this case, and other important information. What I found really interesting was that some of the examples of the accuracy from some standard models was also included. Note that the accuracy was approaching 22%. That didn't seem very good, but as we've talked in class, the modeling of this type of data can't really be compared with the accuracy we see in more parametric models. So keep this number in mind when we start looking at our model accuracy for the CFAR data set. For part 2, we were advised to utilize the Canadian Institute for Advanced Research CFAR10 dataset. It is smaller in storage size than the Stanford Dog dataset, but contains many more images. It is just that the individual images are smaller in dimensions at a consistent 32 by 32. There are 60,000 labeled images with 10 classifications. You can see a list of those classifications on the right with a sample of images from each. Of course, as you can see, they are in color, and this is also apparent based on the depth value of 3. It is also important to note that the classifications are balanced with 6,000 in each classification. There is no imbalance in the classifications. Similar to the Stanford Dog dataset, the CFAR10 dataset is also supplied with a pre-built list of training and testing images. There are 50,000 training and 10,000 test. We'll talk a little more about the images in more detail in part 4. The initial activity of part 1 was to download the dataset from the class Google Drive. I did this using the Google Download option for the whole folder, which resulted in a zipped folder that I then uploaded into my Google Cloud Platform virtual machine. I performed this using the Google Cloud Console Secure Shell, which you can access directly from the VM instances list on the console. The upload option is accessible from the gear icon in the top right of the Secure Shell window. After uploading, I did have to unzip and move the file to my Jupyter notebook using the Linux unzip and mv commands. Once uploaded, there were some predefined functions used to access the data. There were 5 data files, and each contained a NumPy array with 10,000 rows and 3,072 columns. Each row of the array represented a single 32 by 32 image in the form of red, green, and blue pixel values. The first 1,024 columns were the red values by image row. So columns 0 through 31 represented the red values for the first row of pixels in the image, while columns 32 through 63 represented the second row of pixels in the image, and so forth. The second set of 1,024 columns were the green values by image row. And finally, the last set of 1,024 columns represented the blue values by image row. There was also a meta file that contained the associated image labels. We utilized the pickle command to access the data. The pickle Python module is used to serialize or deserialize, in this case, an object to convert it from a byte stream into the object, or again, in our case, the image arrays. We utilized the transpose option to move the red, green, and blue values we saw in the array earlier for row to be grouped by pixel. So we have the red, green, and blue value for pixel 1, followed by the red, green, and blue values for pixel 2, and so on. If you recall, the red, green, and blue values of an image are represented by numbers between 0 and 255. We don't want a dark red at 255 to have more influence or weight than a very light red color at 0, so we normalize. We do this by dividing the color values by 255, so all color values are between 0 and 1. Since we have classification data, we perform some one-hot encoding as well. We'll use these functions by calling them to set up and pull batches during our model generation phase. There are a number of consistent steps performed for TensorFlow model generation, and we'll run through each quickly in this section so we don't have to cover each time we build our different models. We've already talked about obtaining and setting up the data for processing. We've shown that a training and test set have already been supplied in our data set, and we've discussed normalizing the data and one-hot coding for our labels. The next step is to set up some supporting functions that we can call to facilitate initializing our bias and weights, defining layers, and so on. From a modeling standpoint, we'll then set up some variable placeholders, build our model using the functions we just talked about, specify some optimization options, and then run our TensorFlow session to compile and fit our model. Finally, we'll do some prediction and evaluation of the results. There are a number of supporting functions we utilize when working with TensorFlow models. As we learned in the first half of the class, Keras is a front end which can be utilized with TensorFlow to facilitate model creation. It is easier and more straightforward. However, it does hide or mask some of the behind-the-scenes activities of the model. TensorFlow allows these activities to be controlled and provides more insight into the inner workings of the convolutional neural network. This includes things like initializing the weights with random normal values and the bias with constant values. A convolutional neural network consists of basically 2 networks, a convolution network for feature extraction and a fully connected network for classification. We'll see more on this when we build our first CNN, but we can use these additional supporting functions to build the convolutional layers and perform matrix multiplication, as well as executing the activation functions within those layers. Within the convolutional network, we also perform spatial reduction. So we need a pooling layer as noted on the right. This 2x2 pooling layer reduces the height by half and the width by half. So a 32 by 32 image would be reduced to 16 by 16 through one pooling layer. As we discussed earlier, the convolutional neural network consists of two networks, a convolution network and a fully connected network. So we also need functions to define this portion of the network as well. Again, note we perform matrix multiplication and apply bias within this layer to implement the mathematics of the neural network. We also need to create some placeholder variables for our image input values. A 32 by 32 by 3 for the height, width, and depth, as well as a placeholder for our output of size 10 to contain the output probabilities for each of our 10 classes. Next, we'll build the individual layers. As we discussed, the convolutional neural network is really two cooperating networks. The first performs the image convolution or feature extraction along with spatial reduction, while the second takes a flattened input into a fully connected layer for classification of those extracted features. So for the first portion of the network, we'll call those supporting functions created earlier to build the first convolutional layer. In this case, we are using an image filter of 5 by 5 to focus on areas of the size in order to extract importance using the matrix multiplication we referenced earlier. Note the input of 3 channels, red, green, and blue. We build the convolutional layer, apply a ReLU activation function, and then build a pooling layer. We repeat this process for as many layers as desired. Before feeding into the fully connected network layers, we need to flatten the data using the TensorFlow reshape function. Note that in this case, we performed 2 pooling layers, so our image size was reduced from 32 by 32 to 16 by 16, and then to 8 by 8. Therefore, the input to the flattening layer will be 8 times 8 times 64, with 64 being the number of outputs from the last layer. After the output from the last layer of the first network and the convolution network is flattened, we can feed it into the second network, the fully connected neural network. Similar to the earlier process, we call the supporting functions to build the fully connected layer and specify an activation function. We also add a dropout layer to minimize overfitting and specify a percentage of the output we wish to hold, or conversely, what percentage we want to drop, using the TensorFlow dropout function. And finally, we create an output layer of the predictions. Remember, these predictions will represent the probability that any given image falls into this classification. So it's not a value of bird or cat. It is a set of values for bird at 50%, cat at 25%, dog at 25%. We also define some measurements for accuracy and determine the average probability error across the classifications. In this way, we can identify which classification has the highest probability of being the correct one. In this section, we also define our optimization and learning rate. We've defined our models and set our optimization methods, so now we are ready to run our model to generate predictions and evaluate. First, we initialize our variables using the global variables initializer function, and then execute our TensorFlow session to train the model. As we train for 5,000 steps, we also check our accuracy every 100th step. Note the variable called matches, which is picking out the prediction with the highest maximum probability as the identified classification for all the test images and computing against the actual value to report whether the value is matched or not. I'll reference this in the future slide as we go to report on the individual classification accuracy. I added a list to append each accuracy value for easier reference, and we'll show some graphs of that data as we progress through the comparisons. Here's the code that will generate the output from the accuracy list in the form of some graphs and a CSV for future reference. We will use this for comparisons and evaluation of our various models. Okay, so finally we're getting to the good part. In part 3, we were asked to construct a model for the CFAR10 dataset that was comparable to one we built for the MNIST dataset in an earlier homework. In this case, you can see a graphical representation of the network on the top right and a description and parameter information for each layer in the lower table. From left to right, we can see our input as an image from our CFAR10 dataset. Remember, you don't count that as a layer. If you recall, it was color, so there were 3 input channels in our first layer, the first convolutional layer. We are choosing to process with 32 neural nodes using the ReLU activation function. Note that we are also using a 5x5 filter or image kernel to pick out the important features in each of these 5x5 areas within the 32x32 image. Then for the second layer, we perform some spatial reduction with a pooling layer to reduce the image size from 32x32 to 16x16. We repeat the process for the third and fourth layers. For layer 3, we use a convolutional layer which takes the 16x16 image and 32 inputs to process with 64 nodes. Still using the 5x5 filter, we again use the ReLU activation function. The output from the 64 nodes is fed into layer 4, which is another pooling layer, which reduces the image size from 16x16 to 8x8. This is flattened. If you'll note that 8 times 8 times 64 is 4096, which is the input layer to layer 5. The fully connected layer, using a ReLU activation function, we use 1024 neural nodes for this layer. The 6th layer is the dropout layer using the 50% dropout rate. And finally, we output with the 7th layer, which utilizes the softmax function to classify the images into one of the 10 classes. So this 2 convolution with 2 pooling layers model accuracy didn't seem that good. The accuracy after 5,000 steps was 67.5%, and the maximum accuracy was 68.6%. However, if you recall the earlier conversation regarding the accuracy of the Stanford Dogs dataset being 22%, then it puts a more positive spin on these results for the CFAR dataset. And again, as discussed in class, the accuracy achieved in parametric models with non-image data can't really be compared with neural network big data images. Let's compare with the MNIST dataset of homework 4. In part 4, we were asked to compare the results of the 7-layer networks of the MNIST and CFAR10 datasets. Both were 7 layers with 2 convolutional neural networks and 2 pooling layers using a 5x5 image filter. However, the accuracy was dramatically different. As seen in the yellow line in the graph on the top right, the MNIST dataset achieved a very high degree of accuracy at 99% after a few steps. However, the CFAR dataset accuracy shown in blue was quite different, with a maximum accuracy of only 68.6% even after 5,000 steps. It was also interesting to note that the MNIST model was quick to achieve this high success in classification with almost a right angle, where the CFAR model had a more gradual curve in the learning process and achieved some consistency after about 2,500 steps. I attributed much of the difference in the performance of the models to the complexity of the images. Obviously, the resolution was different. MNIST actually had a lower resolution at 28 by 28 compared to the CFAR dataset at 32 by 32. But even so, the digits in the MNIST dataset were the primary focus of each image. They were in black and white, and there didn't appear to be any background distractions. The model could focus on the aspects of what made a digit a 1 or a 7, for example. However, for the CFAR dataset, even though it had a slightly higher resolution, the complexity of the data negatively impacted the model accuracy. Some examples of this complexity are the similar objects being different colors, such as the white and yellow car. The variations in size, such as the really tiny plane flying in the distance versus the large plane on the ground. The different backgrounds, such as the sky, water, branches, and so on. In addition, the object positions and scale were different, such as the chicken with a full body versus the ostrich with just a head presented. I would argue that the complexity of these images had an adverse effect on the accuracy. So again, perhaps the 68% accuracy wasn't too bad after all. Based on those results in Part 5, I elected to redesign the model with a focus on 3 areas: addressing the resolution and complexity by attempting to reduce the filter size to drill down into more of the image details. Initially, I had added a 3 convolution layer and pooling layer, but the 3rd pooling layer made the final flattened input only 4x4, which seemed worrisome. However, after the class discussion and the insight that a convolution layer didn't require a pooling layer, I focused on not reducing the final image to only 4x4. So the major differences were the filter was changed from 5x5 to 3x3, and the 2 consecutive convolution layers with no pooling layer in between. Since overfit didn't seem to be a risk, I also reduced the dropout rate slightly. This resulted in an 8-layer network comprised of 3 convolution layers and 2 pooling layers. The results were slightly better. After 5,000 steps, the accuracy was 69% with a maximum of 70.6%. I was really troubled that I couldn't see the individual classification accuracy. I researched for some time attempting to add a confusion matrix to the TensorFlow session, but was not successful. However, I did find a reference to how to access the TensorFlow variable. So as I mentioned earlier, I made some modifications to the final model script to output the matches variable. That's the true or false indication of whether the test prediction matched the actual test classification. I then took those matches and accumulated them in an array to transfer to a data frame that I could calculate an accuracy by class by dividing the count of the matching by the total in that classification. I'm sure this was not the most efficient method, and the output was really ugly. It did require some manual reformatting, but it did give me the classification accuracy I was searching for, as you can see on the next slide. We can see that the automobile classification was the most accurate at 80%, and the birds were the least accurate at 47%. Based on the images we saw of the different types of birds, sizes, and positions, remember that ostrich head and the chicken full body images? This is probably not that surprising. I checked a number of different models. All the models used the ReLU activation function, had a batch sizes of 100, step sizes of 5,000, and used the atom optimization function. We have talked in detail about the first model, the 7-layer, 2 convolution layers, and 2 pooling layers model with the 5x5 filter. In addition, there was a model with an increased number of nodes in the fully connected layer, 2,048 instead of 1,024. There was no improvement in accuracy. However, it did start with a higher beginning accuracy of 12% compared to the others starting at 10%. The worst performing model was the 7-layer model with the decreased learning rate from 0.001 to 0.0001. This was very confusing because in the prior class with the recurrent neural network and long short-term memory models, the decreased learning rate seemed to improve the model, but that was not the case with this data and the CNN. As mentioned before, the last class lecture and learning that a pool layer was not required for every convolution layer, I had created a 3 convolution layer with 3 pooling layers There wasn't much improvement in the accuracy with the 3 pooling layers, and the image size was reduced to 4 by 4 before being passed to the fully connected layer, and that seemed really small, and I was concerned. So that is when the 3 convolution layer and the 2 pooling layers model was created with an accuracy of 69% and a maximum accuracy of 70.6%. Using the CSV files downloaded from each model, I created a graph comparing each of the 5. Again, the worst model was the blue line with the lower adjusted learning rate, although it did appear to be continuing to grow, and I wondered if I had allowed it to run longer if there would have been an improvement. As we saw earlier, the best model was the purple with the 3 by 3 filter and the 3 convolution layers and 2 pooling layers, which achieved a 70% accuracy. Regardless, after 5,000 steps, they all appeared to be consolidating to the same accuracy range. With regard to my lessons learned and conclusions, there were 6 that I documented. The first is that the CFAR dataset appeared much more complex and difficult to classify. This was because of the variety within the images, like we talked about, the color, size, position, and backgrounds. The second was that increasing the neural nodes appeared to increase beginning accuracy, but did not improve overall accuracy. The third and somewhat surprising observation was that the learning rate didn't appear to improve the accuracy for the CNN model like it had done for the recurrent neural network or the long short-term memory model studied in ADTA5550. That's the recurrent neural networks for sequence data course. However, I think now that it is possible a larger number of steps could have addressed this situation. The fourth observation was that the additional convolutional and pooling layer had only a nominal impact on performance, but that, as indicated in number 5, the addition of the convolutional layer without reducing size by not adding a third pooling layer was a positive result. The sixth and final observation or lesson learned is that even though the accuracy numbers weren't impressive at first glance, based on the complexity of the data and the understanding of neural networks, it is likely that the accuracy of 70% could be acceptable and useful for the classification of the images in the CFAR10 dataset. Here are my references if you'd like to research further or see the data for yourself. If you have any questions or suggestions, please feel free to reach out to me at jamesbanks@my.unt.edu. Thank you very much for your time, and good luck in your future classes and future careers.